Hello, everyone. Today we're going to go through a problem and talk about the concepts associated with that problem as we go through it, specifically about position, velocity, and acceleration. This has to do with one-dimensional motion or one-dimensional kinematics. But again, what we're going to do is we're going to do this in the context of a problem. So this is not typically how you would solve a particular problem, right? There's a particular form for that. When we have a problem, we write down our knowns, our unknowns, what we want to find, and write out our equations, and then put them all together. So here, we're going to do something similar. However, I'm going to take time to explain and go through kind of derivations and things about how positions related to velocity, velocity to acceleration, position to acceleration, and the kinematics that come out of that analysis. Okay, so that's the setup for this. So for this particular problem, we're told that there's a test car that's being run by a computer, and the position of that vehicle as a function of time is given by this equation. Okay, this equation right here. So this tells us a couple of things right at the start. This tells us that we have a definition of position given as, let's see how much space I can take up here. So the position of our vehicle is defined as a position x, right? So we're on an x-axis. So this is a one-dimensional motion, right? So typically we could show this as a number line. Actually, let me do this in green, since that's usually what I do my axes in, right? So we're in one dimension, which means we have a 0 here. This is positive x, and this is negative x. Okay, and it means that the vehicle is going to be moving back and forth, or yeah, because there's a negative in here. So back and forth in this x direction, depending on time, right? So that means that we also have a time component here, where time is given as t. Okay, so that's good. So that tells us that at some time, specifically at some point in time, at some given t, we can find the exact position of this car, this test car, given this equation. Now, the first question here, is put as a 0, what are the units of the constants? And so that helps us understand how this is being described, right? So let me write out this equation here. Alpha plus beta t squared minus gamma t to the 6. Now, again, I've said this in previous videos, but these Greek letters in physics, we use them just as much as regular Latin, Roman letters, right? Our regular alphabet we use, but we also use these Greek letters because, well, basically we run out of letters. And so we extend our vocabulary to include the Greek letters as well. So these are just placeholders, right? These are just variables. These could be any numbers, whatever number we want, but they have specific units. And why do they have a specific unit? Because our position has a specific unit. And what are the units of position, right? Position is a length or a place, so it's a meter. It's a unit of meter for our position. So that means that on this left side, we have meters. On the right side, so here's our equal sign. Now this is called what we're doing right now is a dimensional analysis. Dimensional analysis. We're just making sure that we understand how everything is related here. So if we need meters, right, because we want to end up with the position on this left side, then that means everything on the right has to add up, right, because adding or subtracting has to become meters, which means that immediately we know what unit alpha is in. What units does alpha have? Alpha has a unit of meters, because it's all by itself. It's not being multiplied by anything, which means that if t was 0, for instance, If t was 0, then that means this term would go away. That means this term would go away, which means we would just be left with alpha, which means that alpha must be a initial position of the particle. So now that I've just said that, I'm going to put a little note down here. At t equals 0, x at time 0 is equal to x naught, which is how we define the initial position. X sub 0, or x naught, is equal to alpha. And alpha is some initial position, x naught, right? So let's say that at some initial time, at t equals 0, we have some initial position, which is equal to alpha. Ta-da! Right? That's great. So that's good to know. Now let's do this next part. So we have a meter. We're going to add now this beta times t squared. Assuming that our time is in SI units, then time is seconds, which means we have a seconds squared here, which means that our beta has to cancel out these seconds squared, because we don't want seconds over here on this right side. We only want meters. So that means that the beta has to be a meters per second squared, specifically so that these second squareds can cancel. And again, we're left with meters. Good. And the last piece we have that we're going to subtract this gamma t to the 6th term. Oh, I meant to put parentheses, I'm sorry. The t to the 6th means that we have seconds to the 6th. That's the end of our equation here for our dimensional analysis. But again, we want meters to be the only thing that's left when we multiply these things through, which means we want meters per seconds to the 6th, so that these things can now cancel out. So those are the units of our variables. It doesn't matter what the value is right now. What does matter is that we've established that if these things have a value, have a number, have some amount, that they're going to have units of meters per second squared for beta and meters per seconds to the 6th for gamma. Okay. I guess I'll make this point too. One of the things that we like to do in physics is describe things with equations like this, but only using variables, only using letters, only using Greek letters, because what that allows us to do is solve for it. And once we solve for it generally. So we can replace those variables with any number we want, or any number that fits with whatever we're dealing with. But it keeps our solution open to an infinite amount of possibilities, right? If alpha was given a particular value, say 1, beta was given a value, say 2, and gamma was given a value, say -1, we plug those things in and we only can solve then this problem for one particular set of variables. But if alpha and beta and gamma are open and can be whatever variable or whatever number we want them to be, then that means we have just solved this problem for an infinite number of solutions, which is amazing to think about, right? So that's why we're going to keep it general with this alpha and this beta and the gamma. Okay. All right, but we've established that for our part 0, right? So we've now looked and we've done some dimensional analysis to determine what these units are for each of these things, and we've determined which one tells us x naught, and that's our alpha. So that's great, right? Our initial position. Okay. So if we scroll through here a couple more. So here we wanted units for that first one. That's great. The next one asks about velocity. Part B asks for acceleration. The next one asks for position acceleration when velocity is 0. And the last one talks about average velocity. So before we can go on to complete the rest of this problem, we have to understand what is being asked here. So if our position is given as x, let's see here. So let's do a little hypothetical. So if we start with our x naught, right? We know what that is right here. So we'll call it x naught. And at some later point, we end up at some other position. We'll call it x final and say it's somewhere around here. Doesn't necessarily matter right now. The question is then, how fast did we go from x naught to x final? Well, the way that we can find that is, let's define a delta x as our final position minus our initial position. So this delta means a difference or a change in. So this is a change in our position. We define as our x final position minus our initial position, whatever those values may be. And we'll say that our delta t is some final time minus our initial time, and we'll take our initial time to be 0. And if we want to know the rate at which we change that position, then we divide our change in position by our change in time. This is called the rate of change of position. Or instead of saying the rate of change of position every time, we also call this the average velocity, specifically in the x direction, because we're only talking about one direction right now. So this is the average velocity. If we look at one point or some final point minus some initial point over the amount of time that it took to get from point A to point B, or from x naught to x final. Okay, that hopefully makes sense to you. But now the question is, well, what happens if we take that delta t, right, the amount of time that it took to go from some initial point in x naught to some final point in xf, and that delta t gets smaller and smaller and smaller until it gets so small it approaches 0. Well, that is something that we like to talk about in physics and math as a limit, right? So if we take the limit of this average velocity, specifically it's delta x over delta t, right? What's now happening is that we are scrunching that delta t down, which means that the amount of distance that we're able to move, that delta x is also going to get smaller. But specifically, we're looking at this denominator, and so as this denominator gets smaller and smaller and smaller, this becomes a derivative, or a single point in time, which allows us to then define this as the velocity in the x direction. So dx dt is the velocity at a particular point in some object's motion. So we go from an average, right? So note the difference here. The average, which is this rate of change of position over some amount of time, to an instantaneous, I guess I should write that out, right? This is an instantaneous, I can't spell. Right, so we go from a rate of change, so we have a span of distance and time that we take that ratio of, to an instantaneous velocity, which we look at a specific point in the motion of this particular object, in this case, the car. So that means that we can look at this problem and say, hey, I have an equation for x that is dependent on time. So in order to determine the velocity equation, I can just take the derivative of this equation and get the equation for the velocity. So, gosh darn it, we'll do it right now. Here we go. So our velocity equation is defined as this. Right, the derivative of x, and specifically the time-dependent x equation divided by time. So we'll substitute that in. So we'll have our d dt, we'll substitute in our dx or our x t equation. So we have alpha, we have beta, and we have gamma. We take the derivative of that. We're going to take the derivative of each piece. And we end up with the alpha goes away. Oh, here, I guess I should do this. The alpha goes away because the alpha is not dependent on time, so that goes to 0. This becomes 2 beta t, and this is 6 gamma t to the 5th. Can't forget that negative though. So that means that our equation for our velocity, which is dependent on time because time's in it, is 2 beta t minus 6 gamma t to the 5th. That is now our equation for the velocity. So at any point in time, given a beta and a gamma, we can determine the velocity of this car per this equation. Okay, now let's do another quick dimensional analysis on this, because we already know what the dimensions are for beta and gamma because we established them here. So let me write this out. So alpha has units of meters, beta has units of meters per second squared, and gamma has units of meters per seconds to the 6th, right? So if we come down here and do some unit analysis, velocity, can you tell what units velocity are in? We have it over here. The numerator is a length, a change in length, a change in position, which is meters, and it's divided by time, so that's our rate of change, meters per second. So that means that on our right side, this should come out to meters per second. So let's look at this. Beta is a meters per second squared. Seconds is, or time is now seconds. Woohoo! So that means we end up with a meter per second there. And we are subtracting a gamma, which is a meters per second to the 6th times a seconds to the 5th, which means that we have meters per second again. So that's good. So our dimensions work out. Okay. All right. So that is the relationship between position and velocity. Now, the next question is asking about acceleration. And an acceleration is instead of having a change of velocity over change in time, or instead of having a change of position over change in time, or instead of a rate of change position, we have a rate of change of the velocity. So we can write this now as an average acceleration in the x direction. So a little a is what we use for our acceleration. In the x direction is defined as a change in the velocity in the x direction divided by the amount of time that it took for that velocity to change, also known as a rate of change of velocity. So you'll see this a lot in physics. Whenever we divide by time, it's talking about a rate at which something is moving or changing. I'm sorry, not necessarily moving, but a rate at which something is changing. If you're familiar with watts, watts is joules per second, which again, if you're not familiar with it, that's okay. But a watt is something that we generally have kind of an idea about because that's what light bulbs are typically measured in. But that's a amount of energy per time. So that is a rate of change of energy per time, or how much energy it uses in a given amount of time. Right. So this rate of change comes up often, and so this is just the first instance of it, I guess. But here is our average acceleration, which is the rate of change of velocity over time. Now, the question then becomes, what happens as our delta t goes to 0? right? This is our limit again. So we can talk about the limit of delta t going to 0 for this rate of change of velocity. What does this turn into? This turns into, again, a derivative. A derivative of the velocity with respect to time gives us the instantaneous acceleration in the x direction. So again, we're only dealing with the x direction right now. So this is now the instantaneous, there we go, acceleration. Okay. So now we have well, let's take it one step further here. So if this is the case, we can actually do a little substitution, right? So if our acceleration, the instantaneous acceleration in the x direction, is given as d vx dt, we actually have something that tells, or another equation that tells us what vx is, v sub x, and that's our dx dt. So now let's substitute that in. So we have a derivative with respect to time of dx dt, which means that we have a second derivative of position with respect to time. So this now gives us a direct relationship between our position and how fast that position, or the rate of change in that position, twice over for the acceleration. So we have a direct way to go from a position to velocity to acceleration. And I guess technically the other way, because you can just integrate to get back, right? So this tells us our relationship here between our acceleration and our velocity. So we can do two things for now determining the acceleration of this particular vehicle or car that's being remotely tested by a computer. All right, our acceleration is defined as dvx dt and d squared x dt squared. All right, so we could start from the x equation that we start with and take the derivative of it twice, or we can start with our velocity equation and take the derivative of it once with respect to time. But because we've already done that first one, then we might as well do it here. So we'll use that v here. So we have 2 beta t minus 6 gamma t to the 5th. And we're going to take the derivative of that. I'm not going to write it out completely, but you can go through and make sure that you have it down. This is going to be 2 beta minus 30 gamma t to the 4th is equal to our acceleration in the x direction with respect to time. Awesome. Okay, so again, the importance of writing it this way with our beta and our gamma and our alpha and all of these letters is that we can put in whatever number we want, right? So if we're given that alpha, again, as I said before, if we're given that alpha is some number like 625 meters, that beta is 2 meters per second squared, and that gamma is negative 0.001 meters per second to the 6th, then we can just plug those numbers in and we can get a value at a particular time. Right? So that's the power of doing this algebraically instead of having all of these numbers. I would also challenge you that if you are given numbers in a problem, that you just replace it with something else first, solve it, and then replace those numbers back in, because then you have that resultant that can be used in any infinite number of configurations. Okay. All right. So that takes care of the first few questions. The next question is saying, what's the position and acceleration when the velocity is equal to 0? Okay. Now, there we go. Okay. So now this question is, let me rewrite it down here so we don't forget. What is the position and the acceleration when the velocity is equal to 0. So this is an interesting question because the one thing that we don't know here is time. Well, assuming that we know alpha, beta, and gamma, right? Assuming that those values are known, we're asked for what is x and what is a, what is the position, what is the acceleration when the velocity is equal to 0. So what we can do is say, all right, well, if we know this, right? They say that this is true, then that means we also know that this is true, right? That the equation that describes the velocity has to equal 0. So now we have this lovely equation, all equal to 0, which means we can do some algebra and we can get that 6 gamma t to the 5th is equal to 2 beta t. Okay? Which means that we already have, well, I guess we could kind of tell up here, that one of the solutions is what? That the velocity at time of equal to 0 is 0, right? So if we plug 0 into t, junk, junk, then that would equal 0. So that's one of the solutions. Another solution is if we cancel out one of these t's here, we get a 4th. We now get 6 gamma t to the 4th is equal to 2 beta. I'm also going to cancel out, I should have done the last step, cancel out that 2, so we get 3. So then this becomes 3 gamma t to the 4th is equal to beta. Or specifically, t to the 4th is equal to 1/3 beta over gamma. Now, why would I solve for t? What's the purpose of that? Okay, the purpose is we have established that we want the velocity to equal 0, or rather we want to find the position in the acceleration when the velocity is 0. So we set velocity equal to 0, and because we have an equation for it, we can solve for the time, or the times, at which the velocity is equal to 0. And specifically, the time that the velocity is equal to 0 is, oh, I guess I should write this out more fully. So the velocity is equal to 0 when time is equal to the 4th root of 1/3 beta over gamma. Those are the times, or that is the time, in addition to 0, when the velocity is 0. Now, once we have this, we can then take this time and plug it in to our position, our acceleration, because we want to find that. Okay, so we know the time now that the velocity is equal to 0. So now we rewrite our equations for x, which is equal to alpha plus beta, what is it, t squared minus gamma t to the 6th. There we go. Okay, so that's our position equation. I'll rewrite the acceleration one here just so we have it. I guess it's right there. Minus 30 gamma t to the 4th. Okay, so now we're going to substitute for t equals 0 and t equals, I'm going to do this in exponent, or with the power here. So this to the 1/4, which is the equivalent to the 4th root of. Okay, so now we're going to substitute these in. So now we're going to have something that looks like so at x, when t is equal to 0, we've already established this, which is alpha, but we also have x when t is equal to the fourth root of 1/3 beta gamma. It's going to look a bit complicated, but we'll have alpha plus beta, and we're going to square that, so it's actually going to come out to be 1/3 beta over gamma, the square root of that, minus gamma times the same thing, but it's to the 1/6. So it turns out to be, what's that? 3/2. There we go. So that is our lovely, not pretty equation for the position when the velocity is equal to 0. Now let's look at the acceleration. So for the acceleration at t equals 0, we get 2 beta. Fairly straightforward. For the acceleration when t is equal to the fourth root of beta, 1/3 beta over gamma, it's equal to 2 beta minus 30 gamma times, notice this is t to the fourth, right? That makes it convenient because now we have 1/3 beta over gamma times a fourth times 1/4, which just gives us 1. So that means that we can now multiply everything through. Woohoo! So this is going to look nice, or nicer. Oops. So we now have 2 beta minus, we're going to multiply through the 30 to the 1/3, which gives us 10. The gammas cancel out. We end up with beta, which means that the answer to this acceleration at this later time, I'll say t the 1/4, is -8 beta. Right, so we have a few solutions because we have a couple times in which the velocity is equal to 0. Again, this position vector is a bit messy, but that's okay. These other ones turn out to be fairly nice, right? But we have a complete set of terms for when the velocity is equal to 0. If you have questions, please let me know, and I can go through those questions. I can get back to you. Okay, but if you don't understand it, see if you can rewind it, see if you can figure it out. If not, certainly send me questions. All right, the last question here says, what is the average velocity? So this is our average velocity in the x direction from t equals 0 to t equals 2. So let's remember what our average velocity means. Our average velocity is the rate of change of position, which is our change in x over our change in time. Okay, which means that we are going to look at some final position of x minus some initial position of x, from some final time minus some initial time. So in this case, I'm just going to write this out first. What is our final x? Our final x is equal to an x evaluated at 2 seconds. And then that means we have an initial x at x equals 0. Or I'm sorry, x at t equals 0. That one, again, we already know, which is our initial position x, which is our alpha. For x at 2, we just plug it in. So we have alpha plus beta times 2 squared, or 2 seconds squared, minus gamma times 2 seconds to the 6th. So if we set that all up, we have that this is equal to our final x, which is alpha, plus 4 seconds squared times beta, minus 2 seconds to the 6th times gamma, minus our initial, which is alpha, all divided by 2 seconds minus 0 seconds. Notice now that our alphas cancel out because of that negative there. And so we are left with something that looks like this. 4 times beta to the 2nd squared minus this quantity 2 seconds to the 6th times gamma all over 2 seconds. And that is our average velocity in the x direction. Again, once we're given beta and gamma, then we can just plug it in and we can get a value for it, right? The power of keeping it in some algebraic terms is that it has an infinite number of solutions, depending on what the problem gives us. So I hope that was sufficient to describe to you the relationship between position, velocity, and acceleration as we went through and stepped through this problem. I hope this gave you some techniques to how to approach a problem and look at it. So we'll continue to do this on lots of the other concepts so that we can go through and see how it relates, and hopefully then you can generalize it to any type of problem that you are given. So thanks for watching.